Thank you for joining us for the webinar today. This webinar is Future Proof Your Business, Automating Your DM Shop, your die mold shop. Our presenter today is John Bradford. Many of you have probably worked with him at Makino before. There may be some questions that come up today. If they do, if you will put those in as a direct message, that'll come to me, and I'll make sure that John has all those questions here at the end. And if we have time, he'll get to those, and if not, we can answer some of those questions on the back end after this this webinar. We will be recording the webinar today, so if you didn't quite understand something or wanted to see it again, it will be available on our website in the next week or so. So check back if you wanted to see this again. And with that, we'll go ahead and let John get started. Thanks, John.
Thank you, Lisa, for the introduction. Thank everyone for their time this afternoon to join us. I'd like to start through the presentation, and we'll start with an overview or a summary of the discussions today. So we're going to share our definition, what we consider to be automation, what are the triggers, why and when to automate. We're going to share with you some common popular automation platforms that are employed in the die and mold shops today. We're going to provide you a little bit of where you're at today and where you want to go, and paint a little bit of a roadmap of how we get to the destination that you're desiring. We're going to spend a little bit of time in discussing the importance of process, specifically the machining or manufacturing process related to your components. I'm going to dive into a little bit deeper detail around the process control. I'll share some discussion points and ideas with you around capability and helping you understand the error budget or stack up error that is important to understand. And we're going to share with you some common steps in how other shops that we worked with have implemented automation throughout the workplace, and share with you other considerations that may not necessarily be obvious when we think about automation. So typically we think of automation as any task that is repetitive and a task that can be replaced with an automated device. So whether it's a handling device or a software component, some examples in our daily lives today could be the dishwasher, self-driving car, the automatic vacuum that runs around the house, scaring the pets and running down the stairs. So anyway, those are just some common examples to help you think about automation maybe in a little different way. So some of the trigger points that we commonly talk about are relating to capacity, and this could mean trying to increase your current equipment utilization rate, also looking for ways to get more throughput through your system today without adding any additional resources. We also want to discuss the importance of cost reduction. So this could be direct labor, it could be lost time, possibly relating to bad utilization or poor utilization of existing equipment. This could also, relating pretty directly, is quality enhancement. So specifically having better process control, reducing scrap and waste. Also very common in discussions over the last couple of years is the shortage of skilled labor. So how do we attack that specific element by using a little different approach? And also competitive positioning. So as you're quoting today, as you're marketing your business today, what are your salient points of your business? So we want to look at automation relating to your ability to compete in the marketplace today. So another thing that we like to look at when we're visiting with clients is we want to help them think about how they utilize their floor space today. It's a very, very valuable commodity that you possess is your shop floor, your capital equipment, your people. So are you using that space effectively today? So, how many machines currently sit idle during a shift? Many of you recognize this particular picture as a traditional shop. This is similar to one that I grew up in. So you had a lot of machines sitting around waiting for an operator to bring work to it. So this is not too common anymore, but something that's interesting to look back at. Also, how do you apply your labor today? So again, it's not common, especially in the Americas, in North America, Canada, Mexico, where we have an operator for every machine. We typically cannot, bear that type of operator cost per machine. So this is not a typical model that we see, but an example of something that triggers a thought to say, okay, how am I utilizing my labor today? So we like to examine utilization rate and look at the percentage of time that the machine is in cut compared to when it's not in cut. And then you can break the non-cut time down by the two factors of in cycle, but it may be traveling from one part to the next, or traveling to a tool change position and back, or if the machine is just sitting waiting for work, or it's an operator setting a part up using the machine spindle to set it up. So we want to look a little bit more carefully at why our utilization rate is not at 80, 85% or more. So when we look across a simple chart, we like to look at this chart, and we want to share with you, starting in the left-hand column. This is a traditional standalone machine that is basically set up by an operator without any type of zero-point tooling system. So this machine would require an operator to bring the part to a vise or clamp to the table, and then they would have to probe the part, tram it to find the reference or the datums for that particular part. So the effective production time in this example on an annual basis is about 800 hours. Again, assuming that we don't have, a 20, 30 hour runtime after the part is set up. So this also gives us a downtime of about 1,000 hours for this machine. Now, as we move to the right, you can see the only change that we've applied here is the fact that we've added a zero-point tooling system that allows for quicker part setup, quick in and out. The operator doesn't spend any time referencing, aligning, tramming the part relative to the machine spindle. So we're able to gain about 50% more than just having a machine without integrated tooling. So the next step over to the right is adding a capability to preset offline, meaning that now I no longer have to find my reference on the machine. My machine can be used for cutting only. I don't have to use it for picking up the part. So I have integrated tooling. I know where my 0 point's at. I can pick it up offline, transfer that information and the part to the machine, and I already have that information established. Now, the next step over to the right, we're going to add a material handling device. So this is simply replacing the manual transfer of the material into the machine. So this is helpful where I don't have a man available, or if I'm working, the machine's working overnight or a holiday. This allows me to transfer the material in and out of the machine without an operator present. So you can see the productivity gains each step that we make towards full automation. And then finally, the last graphic in this particular chart is showing the addition of a cell controller or a management system in addition to the physical automation transfer device. So we went from an 800-hour effective uptime to 6,000 hours by adding incrementally these additional pieces to help us improve that utilization rate. So I'm going to share with you some examples that are available that we commonly sell to our clients, install in the marketplace today. So starting out is I just want to help everyone identify and think about the standalone machine. So, this is a standalone machine, CNC control, has some automation options such as tool changer, some control options to give you some unattended operation. Then we would step forward into a single machine or a multiple machine cell being tended by maybe a pallet changer or a part changer. And then our next example is going to be complex cell where we have multiple machines with different types of machining technologies, machining disciplines such as grinding, milling, EDM, in a mixed type of an environment. So these commonly are set up in a linear track arrangement for the automation, for simplicity of placing the equipment on the floor. We typically would have presetting involved in this type of a cell, some type of a material load in and load out station. May or may not have a CMM for some in-quality measurement. And if we do have a CMM, we would have some requirement for parts washing and drying before inspection. And then, of course, we would need to have some centralized management of when we have multiple machines, higher complexity cell. So I'm going to share with you two common interface types that we will typically install. So the first type is a very, very simple. This can be likened to a machine with a tool changer, because in this case, the machine is the master. So all of our programming, M codes, all the commands would come from the machine control. And then the robot or the pallet changer would just simply be the slave to the machinery or to the machine control. So this is what we call the type 1, where we don't have a cell controller. All of your process data is created and managed by the operator through the machine controller. So some examples of this type 1 are, a single standalone machine with a pallet changer. Call it a robot if you want. Then we can also accommodate multiple machines with the type 1 that share the same robot. So in this case, you have to be a little bit more careful about how you isolate your storage magazine for each individual machine, because it's a little bit difficult to manage a mixed carousel if you're sharing the carousel with multiple machines. So without a cell controller, this can be done, but it's a little bit more difficult, and the operator has to be on his toes when he's making the programs. So the next style is what we call the type 2, and this is where we have a cell controller at the higher level of the configuration. So in this case, the cell controller becomes the master of all the equipment in the cell. So your robot and your machine or machines become the slave. So all of your process data is now managed, coordinated through the cell controller. So the benefits of this type of configuration allows for better coordination where we have more complex tasks, more complex decisions to make. So what we think about here is a cell controller has a much better capability to organize all the data that's required. So the operator's not scrambling around. He's not having to make sure all the data and pallet numbers, NC program numbers are all coordinated. All of that worry is taken off of the operator's shoulder with a cell controller. So primary point, simplifies his task, enhances the machine uptime, allows for a quick change of priority throughout the day, and provides for a dramatic reduction in operator error, especially as things get more busy and he has to manage more data. So some examples, we have many cells in this example that have just a single machine with a single robot, but they use a cell controller to manage the program pallet schedules, manages and keeps track of error, warnings, machining stoppages. Also provides us the ability to track and manage performance of the cell as well. So this is a simple example of a type 2. And these can expand as large as you want. So we have some installations here in the States that are up to 30 meters long with 9 or 10 machines. So this is an expanded type 2 cell with a linear track layout. So how do we get there? So we've given you a couple of examples, given you some scenarios, different machine layouts. But really the question is today for you, you know where you're at, you know where your shop is at today, you know where your people are at, you know your capabilities. So what we want to do is help paint a little bit more detailed step-by-step example of how you might consider getting to your goal. So we think about the starting point of this chart of where we're at today. The last step your destination may be full automation, meaning that you've got a full vehicle transfer system, maybe with a complex cell controller, or your destination could be anywhere along this stair step. So I just want to step you through this because we feel that the first step really needs to be focused around standardizing your work holding and also looking at how you execute your offline programming today, because these are some really important components in eventually reaching full automation. So the next step that we typically recommend is looking at a closer examination of how you're optimizing your existing equipment. So examples would be, looking at how, are you fully taking advantage of your tool changers, all of your spare tooling functions? Are you using all the control functions that allow you to walk away from the machine and run it reliably? And a very important point is, have you stabilized your machining process? Meaning that you can repeat the same process over and over, or if you can run the first part successfully without a failure and meet your target tolerances and your other objectives. So standardization of the process, or stabilization of the process. The next step is we really want the customer to audit their current machine utilization and also their current cost structure. So are you efficient at given steps along this process? So audit your utilization rate. Also look at whether or not you're getting unmanned machining capabilities, and are you successfully able to manufacture a part without failure? Do you know where your tool life thresholds are at? Are you achieving unmanned capabilities in a reasonably efficient manner or not? The next step is looking at your standardization of any of your processes that are involved in manufacturing your part or your end product. So do you have practices and standards in how you execute each step of that? Are you able to set up your parts and your tools completely offline? That is another important step to embrace and to get good at before you move along to the next step. And again, keep in mind, we have not even talked about automation yet. We're just getting the fundamental steps in line before we move to automated material transfer, and then finally automated data transfer and data management. So this is a stair step that we challenge each of you to look at and think about where you're at along this curve. So also the importance of your process. Our process basically is how we do something, how we properly execute each task along the way to reach a successful result. And also what's important is that your process excludes the wrong way to do something. So that's part of the learning. But if we document and learn properly, we are able to have a way to do something. So I think about this as, cooking, a recipe book. I like to know that when my wife or myself makes a dish, it's going to taste reasonably good. So a recipe or a process is nice to have. So the documentation of your process step is important because it allows your people with the experience, the learned experience, to not only teach someone else, but also document and have some procedure that you can pass along so that when you repeat this task again, it's going to be efficient. You don't have to repeat and try the things that didn't work the last time. So this is helpful for training, for traceability of your manufacturing. And very importantly is we want to have a defined workflow. So your flow chart or your workflow can just be simple as, 5, 6, 7 steps that you take each time to perform a task. So this is nice because once you have your process flow chart, you can teach someone, you can document, and, even when you get into full automation, you can actually integrate that into software logic. So your process controls involve your stability of your process. So your variability, and your variability comes from many different things, such as your shop temperature, your machine tool, your tooling and your tool deflection, your machining process, and also how you inspect and what's the uncertainty of your inspection process. So also I want to help everybody think real briefly about in automation, you typically need a longer time before you set up from when you set up a part to when you machine it. So if you set up a part on Monday and you machine it on Thursday or Friday, you need to know how much your temperature has changed from the time you initially basically got your datums for your part that might be set up on a pallet. So also we have to understand predictability. So can you hit your target the first time? Because in a die and mold shop or an environment, we don't have a drawer full of 100 parts to practice on. So you have to have a reasonably good idea of your predictability. So what I like to think about is your solid model is the perfect digital scenario. And as you pass that digital model through your shop, how much variation from your digital model are you going to get through your machining process, through your inspection, and all the other steps? So you want to understand your predictability. So can I hit my target the first time or the fewest number of times possible? Because now my parts are high value and I have a low quantity. And then the last thing I'd like to think about is what is your repeatability relative to your accuracy? So we think about your machine tool stability, your process stability, and your measurement technique. So here we think about the first scenario where you have a low accuracy, but you have high repeatability. You can automate that fairly easily if you make an offset change. Second scenario is where you have high accuracy and high repeatability, which is very desirable to have that scenario. And then examples 3 and 4, you start to get more scatter, which means you may have some machine or process variability. So you need to really understand what your contributors are to your repeatability and your accuracy. So capability is really important when you're building an automation environment or planning an automation environment, because you need to understand how much contribution each element will have to your final tolerance. So we like to think about your contributors again from your tooling, your machine process, your cleaning, if it has some thermal additions to your part, how much change is happening in your facility. And then what we do with this information is we like to create a stack up or an error budget to make sure that, hey, if I'm going to have a mill, an EDM, and some other elements within the cell, how much error stack up am I going to get? So we want to make a calculation around your tooling, preset errors, your milling machine process error. And then at the end of the day, what is your accumulated stack up? And if you need to get below this stack up, you need to think about, well, what items do I need to take out of that equation to meet my tolerance requirements within my shop for these particular parts? So practical capability, if you think about 10 microns or 4/10 or just under a half a thou, that's actually reasonably, it's can be challenging to reach that in a fully automated approach. So you need to really look at these individual contributors pretty carefully to think about this when you're planning your automation cell. So automating in the die mold shop. So a lot of people feel that, well, this can't be done. It's only for production. But if you think about the fact that if we have a defined, predictable, and repeatable process, then you can automate that process. So typically in your shop, you want to start with defining your goals for your business. So whether you're targeting efficiency, delivery, utilization rate, cost, unattended machining, quality enhancement, you need to determine what that is. And then communicate that to your team, and communicate this often. So you want to identify what your message is, what processes you're going to attack, what machining elements that you want to have involved. And then what we look at is, we look at this from a company-wide perspective, because you want to have as many steps in your process involved with automation so that you can have a seamless transition from process to process. So this includes starting with your material mounting schemes, starting at your design to include your pallet, your integrated pallets. You want to maximize your spindle time, faster setups, help that operator get to that start button as quickly as possible. That's really what we're trying to do, and then maximize the time or optimize the time that the machines are running. The machine tools have to be predictable and repeatable. Don't attempt to automate everything. And you have to understand your error budget and your stack up. Does that stack up fall under your error budget that's allowable? And your employee communication to your employees and everyone in your organization. Make sure you reinforce the message and the company vision that you laid out in the previous slide. Maintain a solid supplier relationship, because you're going to need them when they start installing the equipment, integrating the automation, executing the applications automation process training. So that the relationship and trust with your suppliers has to be sound and seamless at this point. So generally, we recommend starting small, manually automate first. That just simply means that start with your integrated tooling, manually transfer your parts in and out to the machine, start trusting the tooling, automate your lowest risk operations first. Graphite electrodes are a great place to start. Lower risk as far as if you break a tool, you break an electrode, it's generally fairly inexpensive. But what you do here is you're able to get quantities, unattended time, and you're developing trust in the automation process. So start to experience the efficiencies of this at a smaller, less risk scale. Audit your machine utilization. And you start developing the mindset. You start to schedule accordingly. You start to plan the work accordingly. And you also realize and accept that this is going to be different. And you can also start exposing other people in the shop to what you're doing, communicate those successes. Also, the last bullet point here is understand that your majority of your challenges are going to be cultural shift, cultural transition. The technical challenges, the technical obstacles typically have already been solved. The challenge here will be helping your staff and your company realize what it is, communicate where we're going, and help them along that stair-step transition that we talked about earlier. Help them through each step of learning and gaining that confidence and competence in each of those steps. But last bullet point's important. Please keep that cultural challenge in mind. So standardization, I just want to revisit this. The very foundation of this slide, number one, is your procedures and your standards need to be developed by your veteran employees. These are the people that bring the skill, the knowledge, the years of experience years of learning what doesn't work, they are the foundation of our process standardization. So help them understand and then integrate them into this solution so that they can teach the younger people, they can develop the process standards in the process documentation to help make, but basically they lay the foundation for this success. So basically you've got your integrated tooling system. This is an example of a shop that basically has dedicated setup areas, storage for their pallets. So again, they are planning across the shop. These are my pallets. This is where I'm going to store them. They have dedicated places in the shop. They're not just put in drawers or laid on top of toolboxes where we have room for them. But the steps in a workplace are start at the design and tool path phase. Again, my pallets in this case are part of the model, part of my design. Second step is have your materials prepared, mounted in a specific area in the shop that is designated for setup and pallet preparation. The third, these are just some examples of various fixtures that can be mounted to the pallets. Obviously, we have conventional vices and multiple V-block fixtures mounted to the pallets that are going to be transferred into the machine. We also have to think about how we're going to communicate across the different processes, steps from one area of the shop to the next. So this particular company uses, in this case, different colored marking pens, different types of tracking sheets, different communication tools on the tracking sheets to help communicate the status of the materials to the next people that are going to touch these parts. Third step is just you're going to identify the pallets, and these, if these are traveling through the shop, you're going to have some type of an RFID tag that identifies this pallet and this part relative to the manufacturing task. So this is the registration step. Fourth step is these pallets will go to a designated setup area in the shop where all the offset information is obtained and then correlated to the RFID tag, which is stored in the cell controller unit for the automation. So again, fourth step, presetting. Again, we're not using the machine tools for this. We're using dedicated presetting system. And the fifth step is basically you take the pallets and the materials and you load them into the automation storage unit. So your work, step 1 through 5 is the same on every job, every part. So the process, fifth step in the process is loaded into the storage unit of the automation. You're ready to schedule the work at this point. So once you load the materials in, the automation system scans the pallets to make sure the cell controller knows where they're stored. They are tracked all the way through so they're not lost or confused with another job. You don't want to put the wrong part and pallet in for the wrong NC program. So other considerations, we're reaching the conclusion of the presentation. I just wanted to share with you the other thoughts are the fact that we are asking our staff members that are preparing, planning, programming, they're going to be working offline of the machines now with this new approach, this automation approach. So we have to give them all the offline tools to plan and simulate all the machining processes as effectively as possible offline. So whether this is milling, sinker EDM, wire EDM, we want to have them be able to simulate and visualize all the movements of tools, slugs, potential collisions well in advance of that part ever making it to the machine. So again, this not only protects the machines, but it also makes sure that our manufacturing process flow never stops. So if we have job 1, let's say it stops running because of a collision Friday night, well, that means jobs 2 through 10 don't run through the machine either if the machine has to stop. So this is a really important part of keeping your part flow and your manufacturing flow continuing through the machines. Not just protecting the machines with visualization, but making sure that we keep our manufacturing flow consistent. So if you are thinking about automating your wire EDM, you have to think a little bit deeper about your program strategy, how you're going to manage and hang your slugs, how you're going to process the slugs when operators are available. So you also have to make sure that you have a reliable automatic threading system so that you're not missing threads. So these are some fundamentals that you have to think about, even if you're not automatically transferring parts in and out of the machine. You still have to do this in an unattended machine mode. We have to have a highly reliable and low maintenance guide system so that we're not having to stop the machine every 30 to 40 hours to clean guides. And also, as we start thinking about extended run times, we want to think about the stability of the machine platform over time. So thermal drift, positioning accuracy, every aspect related to long machining times. Low maintenance overall machine system. So that could be your lower arm slide plate. It could be filtration, threaders. You also have to think about your access to the machine zone, both by your operator and your automation system. So can both the operator and the automation system coexist in loading and accessing that table? You also have to make sure you have enough wire spool capacity to run through a weekend or overnight. Your energizer plates as well. Material management. This is something that's not often considered, but how are you going to cut apart, take it out of the machine, and have it sit on a shelf without rusting or oxidizing after it comes out of the machine? So you have to think about how you're going to manage your material after it's been cut. So in summary, to compete in today's environment, we believe that automation and effective automation is imperative. We also want to encourage you to engage with your suppliers. Look for a credible, knowledgeable, experienced supplier that has knowledge and experience in integrating and planning automation systems. We believe through our experience, and Makino has been consistently involved in automation systems in the die and mold production environments since the late 1980s. So we have a vast amount of experience in not only works, but also what doesn't work. So we are able to help guide clients through potential pitfalls and basically, advise to areas that will and will not work effectively as you consider automation investments. So again, we believe that the automation, if properly planned, is low risk. We also want to help remind you that all tasks should not try to be or attempt to be automated. It's not cost effective in some cases. We also want to remind the audience today that a stable and controllable process must first be achieved before we continue too far down the path and think about automating a task or a process. So first step is having process control. We believe the time is now. And with that, as Lisa had indicated at the very beginning, if you'd like to submit questions, please do that through the interface, or you can also email me directly. I believe my email address is listed in the first slide. If you don't have that, it's just simply john.bradford@makino.com. But with that, we have a couple of questions that came in. One question that I'd like to answer is, how long does it take for a shop to effectively implement an automation system once it's installed? So this varies from situation to situation, and a lot of it's dependent upon the complexity of the automation environment that's being installed. A simple type 1 system where you have a machine as master, a single standalone cell, normally you can start realizing effectiveness within a period of 1 to 3 months. You should be able to gain relative maximum efficiency within a period of 3 months, as long as there is a controlled machining process that's somewhat defined, and the operator has relative competence in that. So 1 to 3 months, you should be able to ramp up relatively quickly to that, realizing full optimization in that particular system. The longer periods of times come when we have a more complex system where you have multiple machine processes and multiple steps involved, multiple operators. That becomes 6 to 9 months. 9 to 12 months is not uncommon in that type of scenario. So with that, I'm going to go ahead and conclude. We're about 10 minutes over. I apologize. But again, if you'd like to submit questions afterwards, feel free to type those in, and Lisa will collect those and we will respond back to you. And with that, I would like to thank everyone's involvement and your patience today. Thank you again for joining us.